Many anglers spend years obsessing over knot topology, searching for the specific geometry of a Palomar, an improved clinch, or an Orvis that will finally hold against a trophy fish. When a leader eventually snaps, it's easy to blame the shape of the knot or assume the material itself was part of a bad batch from the factory. But if we look at the physics of these failures, we often find that the geometry of the knot wasn't the issue. The structural integrity of the line appears to have been compromised before it ever saw a fish. This suggests the primary cause of failure isn't the fish pulling, but rather the microscopic damage caused by the angler while tying the knot. To understand why, we have to look at polyvinylene fluoride, or PVDF. Commonly known as fluorocarbon, this is a high-performance semi-crystalline polymer. It's an incredibly dense material built from a molecular chain that is naturally abrasion-resistant and hydrophobic, meaning it won't absorb water and lose strength over time. However, PVDF is also very rigid and acts as a thermal insulator. Because it has extremely low thermal conductivity, it cannot easily dissipate heat into the surrounding environment. This creates a direct conflict between the material's properties and its application. The mechanical action required to use this rigid line, bending and cinching it, triggers a reaction that can compromise its own molecular architecture. In rigging, the severity of a bend is measured by the D/D ratio. When we force a rigid line to bend sharply over itself, we are moving the material far beyond its simple tensile limits. This causes a phenomenon called ovalization. As the line bends, its circular cross-section flattens under the pressure. This flattening creates a severe strain gradient. The outer edge stretches to its limit, while the inner edge is crushed by intense compression. This three-dimensional contact pressure map proves the result. The bright high-value areas in panel B show that where the strands overlap, they create immense, highly concentrated pressure points. This geometry turns a uniform polymer into a highly stressed structure, and at this point, the material is primed for damage the moment we add friction. This is the dry pull. We see it here as a knot is forcefully cinched without lubrication, grinding the dry surfaces together. This is a tribological event. The polymer strands are sliding past each other while being subjected to those immense contact pressures we just saw. That intense mechanical friction is converted into heat. Because PVDF is such an effective thermal insulator, that heat doesn't bleed off into the air or the rest of the line. It stays trapped right at the interface of the sliding strands, leading to a violent spike in temperature deep inside the core of the knot. By tightening the knot too fast, the angler has effectively created a microscopic thermal bomb that attacks the material from the inside out. In a fast, dry pull, the localized temperature can easily skyrocket past the melting point of the polymer, which for PVDF is as low as 117 degrees Celsius. This causes the stick-slip phenomenon. The superheated, semi-melted surface of the line bites into itself, carving deep microfractures and gouges into the polymer backbone. When this happens, the knot isn't just tight, it's fused and structurally melted, wounded before it ever has to face the weight of a fish. The solution is to change the thermodynamics of the pull. We use the same knot, but we lubricate it with water or saliva before tightening. The liquid isn't just there to make the surface slick, it acts as a thermal heat sink. It lowers the coefficient of friction while simultaneously absorbing and dissipating the thermal energy generated by the sliding strands. This allows for a flawless physical seating. The strands slide into place without the heat spike, keeping the surface of the polymer smooth and intact. By managing the heat, we ensure the polymer matrix remains at 100% strength, ready to handle the maximum load it was designed for. Symmetrical knots like the Palomar do help distribute stress, but that geometry can't save a line that has already been heat damaged. Ultimately, a durable connection depends on thermodynamics just as much as topology. If you treat your gear like an engineered polymer system, choosing a symmetrical knot, lubricating it, and pulling it slowly, you allow the material science to work the way it was intended.